Tonight, we're going to answer a question most people never think to ask. How cold is space? You might think you know the answer. Obviously, colder than anything on Earth. But the real answer is far more extreme than that. Less than 3 degrees away from the lowest temperature that can exist. And it's everywhere. It's cold in ways that break our everyday understanding of temperature, that change what matter is, and that push physics to its strangest limits. And by the end of tonight, you're going to understand what temperature really means out there in the darkness and what it tells us about where the universe is headed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action. But it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something that most people get completely wrong about space. When people imagine how cold space is, they usually imagine it the way they imagine the cold of a deep freezer or the surface of Antarctica in the dark of winter. Or maybe the thin upper atmosphere where jet aircraft cruise at altitude. They scale up their intuitions. They think, it's probably very, very cold. Colder than anything I've ever experienced. And they're right about that last part. But they're wrong about how it works. Because cold, in the way you experience it every day, operates through specific mechanisms. Heat moves. It flows from warmer things to cooler things through 3 distinct processes: conduction, convection, and radiation. Conduction is what happens when you touch something cold. Heat flows out of your hand and into the colder object. Your fingers on an ice cube. Your bare feet on a stone floor at 3 in the morning. The heat transfers through direct contact from one material to another. Convection is what happens when a cold, fluid air, water, anything, flows past a warm surface and carries the heat away. It's why wind makes a cold day feel so much colder than the thermometer suggests. It's why hot food cools faster when you blow on it. Moving fluid strips heat from surfaces, carrying it elsewhere. Both of these processes require something to conduct through. A solid, a liquid, a gas. They require matter. Space has almost none. In the regions between stars, in the vast, dark, open expanses that make up the overwhelming majority of the universe's volume, there is almost nothing. Not a perfect vacuum. There is no truly perfect vacuum anywhere in the observable universe. But close enough that the difference barely matters for most purposes. A single cubic meter of interstellar space contains, on average, roughly 1 atom. Your bedroom, right now, contains roughly 27 million trillion atoms per cubic meter. The best vacuum chambers ever built on Earth, pumped down to the lowest pressures engineers have ever achieved, still contain billions of atoms per cubic meter. But interstellar space holds roughly 1 atom per cubic meter, and in the vast voids between galaxy filaments, sometimes even less than that. In the vast voids between galaxy filaments, the enormous near-empty bubbles that make up much of the universe's large-scale structure, the density drops even lower. In that kind of emptiness, conduction doesn't function. There is almost nothing to conduct through. Convection has nothing to work with. The mechanisms your body relies on to lose heat, the mechanisms that make a cold winter day feel genuinely dangerous, are essentially useless in the vacuum of space. What remains is radiation. And radiation tells a completely different story about how cold the universe really is. Everything, with a temperature above absolute zero, radiates energy as electromagnetic waves. Your body does it right now, as you sit wherever you are watching this. You're glowing in the infrared, constantly, invisibly releasing heat as radiation into the room around you. The walls and objects around you radiate back. The net exchange of that radiation, what you release versus what you absorb, determines whether you feel warm, comfortable, or cold. This is thermal radiation, and it's the only mechanism that operates in the vacuum of space. In space, a human body would radiate heat outward continuously, but almost nothing would radiate back. But there is something radiating back into that vast emptiness, something that fills every cubic meter of the universe. Something discovered almost by accident in 1964. Two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Laboratories in Holmdel, New Jersey. They had access to a large horn-shaped antenna that had been built originally for satellite communications experiments. They were trying to use it for radio astronomy, making precision measurements of radio signals coming from the Milky Way. But they kept detecting an irritating background hiss. It was everywhere. Every direction they pointed the antenna, the same noise returned. The same persistent, uniform signal, day and night, summer and winter, regardless of where the antenna was aimed. They checked the equipment systematically. They thought it might be interference from New York City, about 50 miles away. They ruled that out. They checked for radio frequency interference from local sources. They pointed the antenna at a nearby nuclear test site to rule out possible contamination. They discovered a pair of pigeons had been nesting in the throat of the antenna, leaving droppings inside. They carefully removed the pigeons, cleaned the antenna thoroughly, and resumed their observations. The noise remained. Identical in every direction. Identical at all times. What Penzias and Wilson had accidentally discovered, what they had been trying desperately to eliminate from their data, was the cosmic microwave background radiation. The faint, cold afterglow of the Big Bang itself. Light that had been traveling freely through the universe since it was 380,000 years old, stretched by 13.8 billion years of cosmic expansion, until it had cooled from a roaring fireball of billions of degrees into a whisper of microwave radiation, barely above the coldest temperature the universe allows. That background radiation fills all of space. It permeates everything. Every cubic meter of the observable universe is bathed in this ancient light, arriving equally from every direction. And it corresponds to a temperature, 2.725 Kelvin. In terms you might recognize better, roughly minus 454.8 degrees Fahrenheit or minus 270.4 degrees Celsius. That is the baseline temperature of the universe. Not zero. Not absolute zero. But the closest thing to it that the natural cosmos has ever achieved on a cosmic scale. And it is still falling. As the universe continues to expand, that background radiation stretches further into longer wavelengths, thins further, cools further. Billions of years from now, it will drop even closer to absolute zero. The universe is on a long, slow, one-way journey toward a cold so complete and so total that it has its own name in physics, the heat death. The point at which all temperature gradients have equalized, all useful energy has been spent, and the cosmos settles into a final, frozen equilibrium from which nothing can ever emerge. But we are getting far ahead of ourselves. To understand how cold 2.725 Kelvin really is, you need to understand what temperature actually measures. Temperature is not a thing. It is not a substance. It is not a fluid that fills objects the way water fills a glass. Temperature is a description. It is a measure of the average kinetic energy of the particles in a substance, how fast they are moving, vibrating, jostling against each other. Hot means fast. Cold means slow. This is worth sitting with for a moment. When something is hot, its atoms and molecules are moving quickly, colliding energetically, transferring kinetic energy to everything they touch. When something is cold, those same particles have slowed down. They're still moving. If they're above absolute zero, they must be, but they move sluggishly, with less energy, colliding with less force. At the temperature of boiling water, molecules are moving at hundreds of meters per second, colliding billions of times per second, chaotic and full of energy. At the temperature of your kitchen freezer, around 0 degrees Fahrenheit, or roughly minus 18 degrees Celsius, water molecules have slowed enough to lock into the rigid crystal structure of ice. But they're still moving. They're still vibrating in their lattice positions. Even frozen solid, matter is not still. The colder something gets, the slower its particles move. And there is a point, a theoretical limit, at which particles would have no thermal motion whatsoever. No vibration, no kinetic energy attributable to heat. That is absolute zero. Absolute zero is 0 Kelvin, which corresponds to minus 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius. It is not merely the coldest temperature ever reached. It is the coldest temperature that can exist. It is the floor. Below it, there is nothing. Temperature itself ceases to have meaning. The background temperature of the universe, 2.725 Kelvin, sits less than 3 degrees above that absolute floor. 3 degrees. The entire temperature range of liquid water, the range in which all known life on Earth exists. The range you experience as the difference between a glass of iced tea and a cup of hot coffee spans 100 degrees Celsius. The universe's background temperature sits within 3 Kelvin of the point where thermal motion itself would stop. That is what space is. That is the baseline condition of the cosmos. Not comfortable, not neutral, almost as cold as anything can possibly be. Now here is where things get stranger than most people expect. 2.725 Kelvin is not the coldest thing in space. Because the cosmic microwave background fills space, anything sitting in open space is bathed in that radiation and absorbs some of it. That means objects in space are not actually at absolute zero. They're being warmed, very slightly, by the faint glow of the Big Bang's 13-billion-year-old afterglow. They settle at the temperature of their radiation environment, roughly 2.7 Kelvin. But there are places in the universe that are colder than that. Dense clouds of gas and dust in deep space, called molecular clouds, can shield their interiors from even the faint microwave background. In the shielded, compressed hearts of some of these clouds, temperatures can drop to as low as 1 Kelvin. The Boomerang Nebula, a young planetary nebula, approximately 5,000 light-years from Earth, has been measured at 1 Kelvin. 1 degree above absolute zero. Colder than the ambient temperature of the cosmos around it. The reason the Boomerang Nebula is colder than the universe's background temperature is that its gas is expanding rapidly outward from the dying central star. And when gas expands, it cools. The molecules do work, pushing against the expansion, losing energy in the process, dropping in temperature as a result. This process, called adiabatic cooling, drives the outflowing gas in the Boomerang Nebula below even the cosmic background temperature. It is the coldest known natural object in the observable universe, a place where the cold of space reaches its most extreme. Our most powerful telescopes need cold to work, not metaphorically, literally. The detectors used in infrared and microwave astronomy, the instruments that allowed us to map the cosmic microwave background, study the earliest galaxies, detect the heat signatures of newly forming stars, are extraordinarily sensitive. They must detect signals so faint that a single photon of infrared light can produce a detectable signal. The problem is that any warm object emits its own infrared radiation, including the telescope itself, including the detector housing, including the electronics. If these components are warm, they generate a flood of thermal photons that completely swamps the faint signal from whatever the telescope is trying to observe. To work, infrared detectors must be cooled to temperatures where their own thermal emission becomes negligible. The James Webb Space Telescope, humanity's most powerful observatory, launched on December 25, 2021, carries a near-infrared camera and spectrographs that must be cooled to around -447 degrees Fahrenheit, or -266 degrees Celsius, about 7 Kelvin. Its mid-infrared instrument, which operates at longer wavelengths and requires even more sensitivity, must be cooled further still to below 7 Kelvin in some of its detectors. The telescope achieves this in two ways. First, it is positioned at a location called the second Lagrange point, roughly 1 million miles from Earth in the direction away from the Sun. From that location, the Sun, Earth, and Moon are all on the same side of the telescope. A 5-layer sunshield, roughly the size of a tennis court, made of a material called kapton, coated with reflective aluminum and silicon blocks, sunlight from reaching the telescope's instruments. On the sun side of the shield, temperatures reach around 230 degrees Fahrenheit or 110 degrees Celsius. On the telescope side of the shield, temperatures drop to around -394 degrees Fahrenheit or -236 degrees Celsius. A temperature difference of over 600 degrees Fahrenheit across 5 thin layers. Second, the mid-infrared instrument is cooled further by a cryocooler, a mechanical refrigeration system that actively pumps heat away from the detectors. All of this, the sunshield, the Lagrange point location, the cryocooler exists for one reason: because the instruments must be cold to see. Because any warmth in the detector is noise. Because the universe speaks in faint whispers, and those whispers can only be heard in the cold. The James Webb Space Telescope is, in a practical sense, the coldest astronomical instrument ever deployed in space. And it is cold precisely because the universe it is trying to observe is cold. Because the light from the earliest galaxies, light that left its source more than 13 billion years ago, has been so thoroughly stretched by cosmic expansion that it arrives at Earth in the infrared range. To see the birth of the first galaxies, you need an instrument so cold it barely registers on a thermometer. 7 Kelvin, 7 degrees above absolute zero, cooled by sunshields and mechanical refrigerators and careful orbital design, all to read the cold afterglow of a universe that was once, briefly, impossibly hot. Cold serves astronomy in another way too. Some of the most precise measurements of the cosmic microwave background were made not from space, but from the South Pole. At an altitude of roughly 9,300 feet above sea level, the South Pole offers a combination of extreme cold and extreme dryness that makes it one of the best sites on Earth for observing microwave radiation. Water vapor in the atmosphere absorbs microwave radiation. Dry air, cold enough to freeze out most of its moisture, is largely transparent to these wavelengths. The South Pole is cold enough that the air holds almost no moisture. The South Pole Telescope, a 10-meter microwave telescope, has mapped the cosmic microwave background with exceptional precision. Its location was chosen specifically because the cold of Antarctica makes the atmosphere transparent enough to see through. Cold enables observation. Cold is not just what we observe. It is part of what allows observation to happen. There is another phenomenon that cold space makes relevant, one that most people have never heard of, but that physicists have spent decades thinking about. It is called the Casimir effect. In quantum mechanics, there is no such thing as a truly empty vacuum. Empty space, even a perfect vacuum with zero particles, is not empty. It is filled with what physicists call vacuum energy, or zero-point fluctuations. Quantum mechanics says that the values of physical fields cannot be exactly zero everywhere. They fluctuate. Even in the absence of any particles, the electromagnetic field fluctuates randomly, with waves of all wavelengths constantly flickering in and out of existence. These are called virtual photons. In 1948, the Dutch physicist Hendrik Casimir predicted that if you placed two uncharged metal plates very close together in a vacuum, the fluctuating electromagnetic field between the plates would be restricted. Wavelengths longer than the gap between the plates simply wouldn't fit. But outside the plates, all wavelengths would fluctuate freely. The result: a slight imbalance in vacuum energy between the space inside and the space outside. And that imbalance produces a real, measurable force pushing the plates together, the Casimir force. It was first measured experimentally in 1997, and the measurements matched Casimir's predictions with impressive precision. This is not a small, irrelevant curiosity. The Casimir effect has practical implications in nanotechnology, where it causes tiny mechanical components to stick together unexpectedly. But more broadly, it demonstrates something profound about the nature of cold, empty space. The cold vacuum of space is not nothing. It is seething with quantum mechanical activity. Virtual particles flickering in and out of existence. Vacuum energy fluctuating continuously. Even in the coldest, emptiest regions of the cosmos, far from any star, in the depths between galaxy clusters, space is not truly empty. It is alive with quantum fluctuations. And those fluctuations have energy. The total energy of those quantum vacuum fluctuations, integrated over all of space, may be related to what we call dark energy, the mysterious substance that is driving the accelerating expansion of the universe. We are not certain of this connection. The numbers don't quite work out in the way they should if vacuum energy were simply equal to dark energy. In fact, there is a famous discrepancy, sometimes called the worst prediction in physics, between the theoretical value of vacuum energy and the observed value of dark energy. But the connection is suggestive. The cold, empty void of space is not passive. It has energy. It has structure. And in some sense, we don't yet fully understand that quantum energy in the vacuum may be what is pushing the universe apart. The cold of space acts, even in emptiness. Now, let's talk about human survival in that cold. Not in an abstract physical sense, but in the very concrete sense of what happens to a human body or to a spacecraft exposed to the reality of space. The human body is a thermal system. It generates heat through the chemical reactions of metabolism, roughly the same power output as a 100-watt light bulb under normal conditions. It loses heat to its environment through conduction, convection, and radiation. And it must maintain its core temperature within an extraordinarily narrow range to function, roughly 94 to 107 degrees Fahrenheit, or 34 to 42 degrees Celsius. Below 94 degrees Fahrenheit, in the body core, hypothermia begins to impair cognitive function. Judgment deteriorates. First, people in the early stages of hypothermia often make poor decisions, including removing clothing, a phenomenon called paradoxical undressing. Coordination deteriorates next. Shivering, which is the body's primary mechanism for generating additional heat, becomes violent and then stops as the muscles exhaust themselves. At around 82 degrees Fahrenheit, or 28 degrees Celsius in the core, the heart begins to develop life-threatening arrhythmias. At around 78 degrees Fahrenheit, or 26 degrees Celsius, the heart can stop entirely. At the other extreme, above 107 degrees Fahrenheit, about 42 degrees Celsius, proteins begin to unfold. Enzymes stop functioning. Cells begin to die. The brain is particularly sensitive to overheating. Heat stroke can cause permanent brain damage within minutes at temperatures above this threshold. The range of survivable core temperature spans barely 13 degrees Fahrenheit, about 7 degrees Celsius, before the machinery of life breaks down irreversibly in one direction or the other. Against the full temperature range of the universe, from billions of degrees inside neutron stars to the 2.7 Kelvin of deep space, 13 degrees Fahrenheit is almost nothing. An infinitely thin sliver. In space, maintaining that narrow window requires continuous, active, sophisticated engineering. If you were somehow placed in deep space without a spacesuit, an experiment that has, thankfully, never been conducted, you would not freeze instantly. This is one of the most persistent misconceptions about space. You would not shatter like a glass dropped on concrete. The near vacuum of space is, paradoxically, an extraordinarily good thermal insulator. With almost nothing to conduct heat away from you, the cooling through radiation alone would be slow by the standards of the dangers that would kill you first. What would happen is complex and would unfold rapidly. Without external pressure to hold them in solution, gases dissolved in your blood would begin to come out of solution and form bubbles, a condition similar to decompression sickness, but far more severe and instantaneous. The moisture on exposed surfaces, your eyes, the mucous membranes of your airways would vaporize immediately. The air in your lungs would rush out. Without oxygen being delivered to your brain, you would lose consciousness within approximately 15 seconds. Brain death would follow within minutes. Your body, once you lost consciousness, would continue to cool through radiation. But depending on your orientation relative to the sun, and whether you were in sunlight or shadow, the cooling might actually be slow. In direct sunlight in Earth orbit, your body might initially absorb more solar radiation than it lost through thermal emission. The danger there would be overheating, not freezing. In shadow, you would cool gradually through radiation. Your body, well insulated by its own tissue and the vacuum around it, might take an hour or more to cool significantly. The cold of space is not the immediate threat. It is the long-term condition. The relentless, patient drain of warmth through radiation over hours and days and years. For spacecraft, this is the engineering reality. Not a dramatic freeze, but a slow, continuous thermal challenge requiring constant management. The engineers who design spacecraft thermal systems think not in terms of dramatic freezes, but in terms of heat budgets. How much heat each component generates, how much each surface radiates, how much each structure conducts between components, and how to keep sensitive electronics within their operating temperature range across the full arc of an orbit. These are not glamorous questions, but they are questions that determine whether a spacecraft lives or dies. Several spacecraft have failed because of thermal management problems. The Mars Climate Orbiter, lost in 1999, failed in part because navigation errors had already doomed it. But thermal environments in the outer solar system have claimed instruments on multiple missions. The Galileo probe that descended into Jupiter's atmosphere in 1995 was designed to survive a controlled dive into one of the most extreme thermal environments in the solar system. It transmitted data for 57 minutes as it fell, before heat and pressure crushed and melted it at depths far below the visible cloud tops. The thermal management of spacecraft going to the outer solar system is particularly challenging because those vehicles cannot rely on solar panels for power. The sun is simply too faint at distances beyond about 5 astronomical units. The Voyager probes, Cassini, New Horizons, and others used nuclear power sources called radioisotope thermoelectric generators. These devices convert the heat from the natural radioactive decay of plutonium-238 into electricity. They also provide a steady source of warmth to prevent the spacecraft from cooling too far. The slow radioactive decay of a few kilograms of plutonium, generating warmth like a tiny nuclear campfire, has kept instruments functioning at distances where the sun is just a bright star. That is what it takes to stay warm in the outer solar system, a nuclear heat source. The cold, out there, is not forgiving. There is a question buried in all of this that most people never think to ask. We say, space is cold, 2.7 degrees above absolute zero. And that sounds like a definitive statement about the temperature of space, as though it were a single, simple property. Temperature, remember, is a property of matter, of particles moving and colliding. In a gas, temperature measures the average kinetic energy of gas molecules. In a solid, it measures the average vibration of atoms in a crystal lattice. In a vacuum, with almost no particles at all, the situation is fundamentally more complex. In interstellar space, there is roughly 1 atom per cubic meter. Those atoms do have a temperature in the sense that they have kinetic energy. They're moving, they're interacting with the radiation field around them. But the temperature of those atoms is not necessarily the same as the temperature of the cosmic microwave background. In fact, the kinetic temperature of particles in some regions of the interstellar medium can be much higher, thousands or even tens of thousands of Kelvin, even while the radiation temperature of the particles is in 10 deg. Region is close to that 2.7 Kelvin background. This seems deeply paradoxical. A region described as cold, yet with particles moving at temperatures of thousands of Kelvin. The resolution is that temperature in a sparse plasma is measured differently than temperature in a dense material. In a gas with only 1 atom per cubic meter, those atoms have high average kinetic energy, but they almost never collide with anything. They cannot transfer that energy to a nearby object through conduction. The energy is there, but it's locked in individual particles with almost nothing to exchange it with. This is one of the deep subtleties of temperature in extreme environments. Temperature, as measured by particle kinetic energy, and temperature, as measured by the radiation field, can be completely decoupled in low-density environments. What physicists really mean when they say the temperature of space is 2.725 Kelvin is that this is the temperature of the radiation field that fills space. An object placed in that environment and allowed to reach thermal equilibrium with the surrounding radiation would settle at that temperature. It is not the temperature of the vacuum itself in some absolute sense. It is the temperature of the radiation bath that permeates the vacuum. And that distinction reveals something deep. Temperature is relational. It describes how systems exchange energy. In a vacuum dominated by radiation, temperature is a property of the radiation, not of matter. The universe has a temperature, but it is the temperature of light, of ancient microwave photons drifting in every direction. The last echo of the Big Bang, cooling slowly across the age of the universe. That is a profoundly strange idea, and it is true. But let's come back to space itself. What actually happens to objects placed in the cold of the void? Because here is where people's intuitions break down completely and consistently. You might assume that if you sent an object into space, a spacecraft, a piece of metal, a human body, it would instantly freeze toward the temperature of its surroundings. That it would rapidly cool toward 2.7 Kelvin and become as cold as the cosmic background. That is not what happens. And the reason comes back to what we said at the beginning. In space, the only mechanism for heat transfer is radiation. And radiation is slow. A shiny, reflective object in deep space, far from any star, will eventually cool toward the background temperature. But it will take a very long time. Depending on the object's size, surface properties, and reflectivity, it could take many hours, or days, or longer to lose significant heat through radiation alone. Objects in space are thermally isolated from their surroundings in a way that nothing on Earth ever is. And this creates situations that seem almost paradoxical. In Earth orbit, bathed in intense direct sunlight on one side, facing the cold void of space, on the other spacecraft experience temperature swings that would destroy unprotected electronics within a single orbit. The sunlit side of the International Space Station regularly reaches temperatures around 250 degrees Fahrenheit, or roughly 121 degrees Celsius. The shadowed side, at that exact same moment, can drop to around minus 250 degrees Fahrenheit, or roughly minus 157 degrees Celsius. A difference of 500 degrees Fahrenheit between two sides of the same structure at the same instant. Not because space is particularly hot or particularly cold in any simple, unified sense, but because radiation is directional, and space offers no medium to equalize temperatures the way air and water equalize them on Earth. There is no convection current to carry heat around the spacecraft. There is no conductive atmosphere pressed against every surface. Whatever the sun hits gets hot. Whatever the sun doesn't hit gets cold. And the two sides are separated by an almost perfect thermal insulator, the vacuum itself. Managing this is one of the central engineering challenges of human spaceflight. The International Space Station has an elaborate thermal control system, large radiator panels deployed from the structure, multi-layer insulating blankets wrapping sensitive components, fluid loops circulating ammonia, coolant between equipment and radiators, heaters to keep cold-sensitive components from failing in shadow. All of it working continuously, automatically, invisibly, to keep the interior at a livable temperature, despite the wild extremes happening just centimeters outside the hull. The spacesuits that astronauts wear during spacewalks are essentially personal spacecraft. They include liquid cooling garments worn against the skin, fans circulating air to manage moisture, and calibrated layers of insulation to manage heat loss through radiation. Without them, an astronaut in direct sunlight would overheat within minutes. In shadow, they would rapidly cool. Space doesn't kill you with a single temperature. It kills you with the extremes, and with the absence of any natural mechanism to moderate between them. Now, let's talk about what extreme cold actually does to matter. Because this is where the physics becomes genuinely extraordinary, and where cold stops being just a number on a scale and starts revealing itself as a force that transforms the fundamental nature of materials. At room temperature, around 70 degrees Fahrenheit, or 21 degrees Celsius, metals are solid, but their atoms are in constant vibration. The electrons in metals are mobile, flowing through the material. This is why metals conduct electricity and heat so well. The bonds between atoms are flexible enough that metals can be bent, hammered, drawn into wires, and shaped under stress. They have what engineers call ductility, the ability to deform progressively without suddenly fracturing. Stress a warm piece of steel, and it bends. It deforms. It might eventually fail, but it fails gradually, with warning, with visible deformation before the final break. Cool that same metal far enough, and everything changes. At very low temperatures, the vibrations of atoms that give metals is their flexibility, slow down and diminish. The crystal structure becomes rigid in a way it isn't at room temperature. Apply stress to ultra-cold metal, and instead of bending, it shatters. Clean fractures. Sudden, with no deformation, no warning. This is called the ductile to brittle transition. And it is not a minor engineering footnote. It is a catastrophic failure mode that has destroyed machines, caused disasters, and altered the course of history. The most infamous example is one of the most tragic. Metallurgical analysis of steel recovered from the Titanic wreck showed that the steel used in the ship's hull had high sulfur content, which made it unusually brittle at cold water temperatures. The water temperature in the North Atlantic on the night of April 14, 1912, was approximately 28 degrees Fahrenheit, or roughly -2 degrees Celsius, just below freezing. At that temperature, the ship's steel did not dent or buckle when it struck the iceberg. It fractured. It broke in a way that more ductile steel would not have. The hull plating cracked and separated, opening seams that flooding water poured through far faster than would have happened with warmer, more flexible material. The cold of the North Atlantic did not cause the disaster, but it made the disaster significantly worse. It changed what the metal was. At the temperatures found in deep space approaching -450 degrees Fahrenheit, or -268 degrees Celsius, this transformation is total. Metals become extraordinarily brittle. Rubber seals, which depend on their flexibility to form tight joints, crack and shatter like pottery. Lubricants that keep machinery operating smoothly solidify or become so viscous they might as well be solid. Gases that are perfectly stable at room temperature liquefy or freeze solid. The nitrogen that makes up most of Earth's atmosphere, a gas so stable and unreactive that it is used to keep sensitive equipment inert, becomes a liquid at -320. degrees Fahrenheit or minus 196 degrees Celsius, and freezes solid at minus 346 degrees Fahrenheit or minus 210 degrees Celsius. In the outer solar system, gases like methane and carbon dioxide, which we encounter on Earth only in gaseous or dissolved form, under normal conditions, freeze into solid ice. On Pluto, the surface is covered partly with nitrogen ice, frozen methane, and frozen carbon monoxide. These are things we think of as gases. On Pluto, they are rock. This is why spacecraft that operate in the outer solar system require extraordinary care in materials, selection, and thermal management. The Voyager probes, launched in 1977 and now traveling through interstellar space, carry heaters specifically to keep their electronic components within operating temperature ranges. Without those heaters, as the probes recede further from the Sun and receive less solar energy, their instruments would fail. Cold does not just make things uncomfortable. At the temperatures of the outer solar system and beyond, cold changes what things are. Let's talk about chemistry. Because what cold does to chemistry is perhaps the most profound consequence of all, and it leads somewhere that almost no one expects. Chemistry, all of it, is driven by temperature. Chemical reactions happen when molecules collide with enough energy to break existing bonds and form new ones. The rate of any chemical reaction depends critically on temperature. Cool something down and reactions slow. Cool something down far enough and reactions stop entirely. Life is chemistry. Every process in your body, breathing, digesting, thinking, healing, every signal in every neuron is a cascade of chemical reactions happening at speeds set by the temperature of your tissues. Your body maintains its internal temperature at around 98.6 degrees Fahrenheit or 37 degrees Celsius because the enzymes and proteins that drive the chemistry of life only work efficiently within a narrow thermal range. Drop significantly below that, and metabolic reactions slow. Your heart rate decreases, your breathing slows, your brain function deteriorates. Drop far enough to the range of 86 degrees Fahrenheit or 30 degrees Celsius in your body core, and the reactions of life effectively stop. That is what cold kills. Not through dramatic violence, through the simple, quiet cessation of chemistry. But here is the profound and unexpected flip side. Because in the cold of space, in those vast, dark, molecular clouds where temperatures hover near 1 Kelvin, chemistry does not simply stop. Something different happens. At those temperatures, molecules lack the energy needed for normal chemical reactions. They can no longer bounce off each other with enough force to break bonds and form new ones in the way chemistry normally works. But they can drift. They can settle. On the surfaces of tiny dust grains, floating in these clouds, particles of silicate minerals and carbon compounds, perhaps a millionth of a meter across molecules, accumulate over millions of years. Ice builds up on grain surfaces, layer by layer. Water ice, carbon monoxide ice, carbon dioxide, methanol, ammonia. And on those frozen grain surfaces, even at near absolute zero temperatures, something remarkable happens. Quantum mechanics takes over. At very low temperatures, a phenomenon called quantum tunneling becomes significant. Normally, for a chemical reaction to occur, the reacting particles need enough energy to climb over an energy barrier to break old bonds before forming new ones. But quantum mechanics says particles do not always have to climb over barriers. they can tunnel through them. The probability of tunneling drops quickly as barriers get larger, but for small atoms, particularly hydrogen atoms, which are the lightest and most quantum mechanical tunneling, remains significant even at temperatures where classical chemistry has essentially stopped. Reactions that would never occur in a warm, energetic environment can happen slowly, through quantum tunneling processes, on the surfaces of cold dust grains over vast spans of time. Astronomers have detected, in cold interstellar molecular clouds, molecules of surprising complexity. Methanol, ethanol, formaldehyde, glycolaldehyde, which is a simple sugar molecule, acetaldehyde, dimethyl ether, formic acid, and in the material ejected from comets, material that formed in the cold outer regions of the early solar system, the amino acid glycine has been detected. An amino acid, one of the 20 building blocks of every protein in every living organism on Earth, preserved in frozen comet ice for 4.5 billion years, formed, in all likelihood, through quantum chemistry on cold grain surfaces in the molecular cloud that preceded our solar system. The cold of space is not dead silence. It is a slow, patient, quantum mechanical chemistry laboratory operating on timescales measured in millions of years. And the products of that chemistry, those complex organic molecules, eventually get incorporated into new stars and planetary systems as molecular clouds collapse under their own gravity. The ingredients that made life possible on Earth may have been forged not in the heat of stellar interiors, but in the cold between stars. The cold of space is not just a barrier to life. It may be one of the environments where the ingredients of life are assembled. Let's walk through the actual temperatures of specific places in the solar system and beyond. Because the range from the Sun's surface to interstellar space is staggering. The surface of the Sun sits at roughly 9,940 degrees Fahrenheit, or 5,500 degrees Celsius. That's the photosphere, the visible glowing surface. The corona, the Sun's outer atmosphere, visible as a pearlescent halo during total solar eclipses, reaches temperatures of several million degrees Fahrenheit. This is one of the enduring mysteries of solar physics. By all basic thermodynamic intuition, the corona should be cooler than the surface below it. Heat flows from hot to cold, not the other way. But the corona is not just a little warmer, it is thousands of times hotter than the surface below. The mechanism driving this is still not fully understood, despite decades of dedicated research and multiple spacecraft missions designed specifically to study it. Moving outward from the Sun, temperature falls with distance. Mercury, the closest planet, has a surface that experiences the solar system's most dramatic temperature swings. With essentially no atmosphere to hold heat overnight or distribute it across the globe, the sunlit surface reaches around 800 degrees Fahrenheit, or roughly 427 degrees Celsius. The dark side drops to around minus 290 degrees Fahrenheit, or roughly minus 179 degrees Celsius. On a single rotation of Mercury, which takes 59 Earth days, the surface traverses more than 1,000 degrees Fahrenheit between day and night. Venus, though slightly farther from the Sun, is actually the hottest planet in the solar system. Not because of its distance, but because of its atmosphere. Venus has a thick carbon dioxide atmosphere that acts as an extraordinarily efficient heat trap. Sunlight gets in. The heat it generates cannot easily escape back into space. The result is a runaway greenhouse effect that has driven surface temperatures to around 860 degrees Fahrenheit, or 460 degrees Celsius hotter than the surface of Mercury at its hottest. And unlike Mercury, this temperature is almost uniform across the planet, day or night, pole or equator. The greenhouse effect on Venus is so thorough that even the planet's night side maintains nearly the same temperature as the sunlit side. Earth sits at just the right distance from the Sun, with just the right atmospheric composition to maintain average surface temperatures in the narrow range where water is liquid and the chemistry of life can proceed. Average global surface temperatures hover around 57 degrees Fahrenheit, or 14 degrees Celsius. But that average masks an enormous range of extremes. Antarctica's Vostok station recorded a surface temperature of minus 128.6 degrees Fahrenheit, or minus 89.2 degrees Celsius, in July of 1983. Air that cold is a direct hazard to breathe. Unprotected metal held at that temperature becomes dangerously brittle. At the other extreme, surface temperatures in Death Valley in California have reached 130 degrees Fahrenheit, about 54 degrees Celsius in summer. Earth's surface range spans more than 250 degrees Fahrenheit between its most extreme recorded measurements. Mars averages around minus 80 degrees Fahrenheit, or minus 62 degrees Celsius. Near the equator in summer, daytime temperatures can briefly reach around 70 degrees Fahrenheit, 21 degrees Celsius. But by midnight, those same locations plunge to around minus 100 degrees Fahrenheit, or minus 73 degrees Celsius. And at the poles in winter, temperatures fall to around minus 195 degrees Fahrenheit, or minus 126 degrees Celsius, cold enough for carbon dioxide to freeze out of the thin atmosphere onto the surface as dry ice. The gas we breathe out with every exhale, frozen solid on the surface of another world. Jupiter's cloud tops hover around minus 230 degrees Fahrenheit, or minus 145 degrees Celsius. But Jupiter's interior is another story. Deep inside the planet, under the crushing weight of all that overlying gas, pressure, and temperature increase enormously. The core is believed to reach temperatures of around 43,000 degrees Fahrenheit, or around 24,000 degrees Celsius hotter than the visible surface of the Sun. Saturn's cloud tops reach around minus 288 degrees Fahrenheit, or minus 178 degrees Celsius. Uranus, the ice giant, with its peculiar sideways rotation, shows cloud top temperatures of around minus 357 degrees Fahrenheit, or minus 216 degrees Celsius. Neptune reaches around minus 393 degrees Fahrenheit, or minus 236 degrees Celsius at its cloud tops, the coldest planetary atmosphere in the solar system. Yet, Neptune radiates about 2.5 times more energy than it receives from the Sun. It has an internal heat source, a remnant of its formation 4.5 billion years ago. Heat stored in its interior leaking out into space, meaning Neptune is actually substantially warmer inside than those cloud-top numbers suggest. Pluto, orbiting in the Kuiper Belt at an average distance of roughly 3.7 billion miles from the Sun, he has surface temperatures between minus 375 and minus 400 degrees Fahrenheit, or between minus 226 and minus 240 degrees Celsius. The New Horizons spacecraft that flew past Pluto in July 2015 gave us our first close-up view of a world that cold what it found was startling. Not a dead, featureless rock. A world of nitrogen ice plains, mountains of water ice standing miles high, a layered nitrogen-methane haze in the atmosphere, possible evidence of past geological activity. Cold does not mean simple. At the temperatures of Pluto, chemistry and physics produce structures of extraordinary variety and unexpected beauty. And then there is interstellar space. Beyond the heliopause, the boundary where the sun's wind of charged particles gives way to the true interstellar medium. At a distance of roughly 11 billion miles from the sun, the background temperature drops to that cosmic baseline, 2.725 Kelvin, minus 454.8 degrees Fahrenheit, minus 270.4 degrees Celsius. The solar system sits inside a bubble of elevated temperature and particle density created by the sun. Step outside that bubble, as Voyager 1 did, crossing the heliopause around 2012, and you enter the cold of the true interstellar medium. The difference between the warmest parts of the solar system and the surrounding interstellar cosmos spans a range that is almost incomprehensible. From 9,000 degrees at the sun's surface to less than 3 degrees above absolute zero in the surrounding space. A single star. A bubble of warmth, surrounded on all sides by the cold of the universe. But even interstellar space is not uniform in its coldness. Before we get to the coldest natural environments in the universe, consider something that reveals how alien the outer solar system really is. We tend to think of the solar system as the sun's domain, a warm, lit, energetic environment governed by the star at its center. And for the inner planets, that's broadly true. But the solar system is vast. The distance from the Sun to Neptune, the outermost official planet, is roughly 2.8 billion miles, or about 4.5 billion kilometers. At that distance, the Sun delivers about 900 times less energy per square meter than it does at Earth's distance. 900 times. The solar intensity that you experience on a clear summer day at Earth's distance would be reduced to less than what you'd receive from a single candle held a few feet away. The outer solar system is not just cold, it is dark. The light of the Sun at Neptune's distance is roughly 900 times dimmer than what falls on Earth. It is still bright enough to be the dominant light source, brighter than a full moon on Earth's surface, but it is qualitatively different from the blazing sun we are accustomed to. This has profound implications for any object at those distances. Without sufficient sunlight, chemical reactions driven by solar energy, the kind that shape atmospheres on the inner planets, slow dramatically. Atmospheres freeze out. Gases condense. Ice becomes rock. The outer solar system is, in a very real sense, a different kind of place. Not just colder, different in kind. The moons of the outer planets have revealed this in striking ways. Titan, the largest moon of Saturn, has a thick nitrogen atmosphere and surface lakes of liquid methane and ethane. Not water. Not anything we would recognize as a liquid on Earth. Methane, the simplest hydrocarbon, the main component of natural gas on Earth, is a liquid on Titan. Because Titan's surface temperature is around minus 290 degrees Fahrenheit, or minus 179 degrees Celsius. At that temperature, methane exists as a liquid, just the way water exists as a liquid on Earth. There are methane rain cycles, methane rivers cutting channels into icy landscapes, methane deltas, where rivers meet shorelines of liquid methane lakes. It is, in the most profound sense, a world with a recognizable geography, lakes, rivers, deltas, dunes, but made of utterly alien chemistry. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, mapped Titan extensively with radar necessary because the moon's thick haze prevents direct optical imaging of the surface. What it found was a world where hydrocarbons do what water does on Earth, where cold has made the familiar alien. Triton, the largest moon of Neptune and one of the strangest objects in the solar system, has surface temperatures of around -391 degrees Fahrenheit or -235 degrees Celsius, near the bottom of the temperature range for solid surfaces anywhere in the solar system. And yet, Triton is not geologically dead. It has active geysers. Not volcanic geysers erupting hot material from the interior, but nitrogen geysers, powered by the sun. Here's how it works. Triton's surface is coated with transparent nitrogen ice. Sunlight, even the pale, faint sunlight at Neptune's distance, penetrates the transparent ice and warms the darker material beneath. That warming sublimates nitrogen ice from below, and the pressurized nitrogen gas erupts upward through the ice, creating geysers that shoot nitrogen gas and dark dust particles several miles into Triton's thin atmosphere. Active geysers, powered by sunlight, so faint that it delivers less energy per square meter than a household LED bulb. This is one of the most remarkable things cold does. At these temperatures, the tiniest energy inputs, amounts that would be invisible on warmer worlds, can drive dramatic geological activity. Because the threshold between solid and vapor for nitrogen is so close to the ambient temperature, even a tiny warmth triggers an eruption. Cold doesn't mean static. Cold means poised on an edge, where the smallest push from one state to another can cause extraordinary things to happen. There is something called the cosmic web. When astronomers map the distribution of galaxies across the universe, what they see is not a uniform fog. Galaxies are not scattered randomly through space. They are arranged in a structure of extraordinary scale and pattern. Galaxies cluster in groups. Groups cluster in larger clusters. Clusters connect along filaments, long, thin streams of galaxies and gas stretching for hundreds of millions of light years. Between the filaments are voids. Vast, nearly empty regions of space where almost no galaxies exist. These voids can span hundreds of millions of light years in diameter. They make up most of the volume of the observable universe, and they are extraordinarily cold. The gas inside cosmic voids, what little there is of it, is at temperatures close to the cosmic microwave background. In some cases, measurements suggest the gas in the largest voids could be slightly warmer than the background due to interactions with radiation. But fundamentally, the voids are cold, empty, and dark. The observable universe has a volume of roughly 415 billion cubic light-years. A light-year is roughly 5.9 trillion miles. The volume of the observable universe is an almost incomprehensible number. And most of it, the vast majority of that volume, is in these cold, dark, nearly empty voids. The structure we see in the universe, the galaxies, the clusters, the filaments, occupies a small fraction of the total volume. The rest is void, cold, empty, near absolute zero. This is the true face of the universe, not the glittering tapestry of galaxies that inspires awe in astronomical images. but mostly dark, mostly empty, mostly cold. The galaxies and stars are the exception. The cold void is the rule. Within those voids, the temperature is set almost entirely by the cosmic microwave background, that 2.725 Kelvin we keep returning to. There is almost nothing else to set it. No starlight, because there are almost no stars. No interstellar gas with its own temperature, because there is almost no interstellar gas. Just the radiation field, just the ancient light, and even that is slowly cooling. Every 100 million years or so, the cosmic microwave background temperature drops by a tiny fraction as the universe expands and the radiation stretches into longer and longer wavelengths. The voids are getting colder. The whole universe is getting colder. But in the voids, there is nothing to slow that process. Nothing to generate local warmth. Nothing to push back against the cold. Just expansion and the slow drift toward absolute zero. Let's discuss one more physical phenomenon that the cold of space makes possible, one that connects the universe's coldness to the ultimate fate of matter itself. Black holes. We've mentioned them already in the context of heat death, but the thermal physics of black holes deserves more attention. For most of the history of physics, black holes were thought to be purely cold objects in a thermodynamic sense. They absorbed everything matter, radiation, energy, and released nothing. Their event horizons were perfect absorbers, the ultimate black bodies. In 1974, Stephen Hawking showed that this was wrong. Using a calculation that combined general relativity, Einstein's theory of gravity with quantum mechanics, Hawking showed that black holes are not perfectly cold. They radiate. Quantum mechanical effects near the event horizon, the point of no return around a black hole, cause the black hole to emit thermal radiation. Very faint radiation. Almost impossibly faint, but real. This radiation is called Hawking radiation. The temperature of Hawking radiation from a black hole depends on the mass of the black hole. Larger black holes are colder. Smaller black holes are hotter. For a black hole with the mass of the Sun, roughly 3 kilometers across the Hawking temperature is approximately 6 times 10 to the minus 8 Kelvin. 600 millionths of a Kelvin. More than 40 million times colder than the cosmic microwave background. So cold that such a black hole absorbs more energy from the cosmic microwave background than it radiates through Hawking radiation. For such a black hole to begin to lose mass, the cosmic microwave background itself would first have to cool below the black hole's Hawking temperature, which requires the universe to continue expanding for a very, very long time. Eventually, the universe will be cold enough that even solar mass black holes begin to lose more energy than they gain. And then the evaporation begins. As a black hole evaporates, it gets smaller. As it gets smaller, its Hawking temperature rises. A smaller black hole is hotter. As a black hole shrinks toward zero mass, its temperature rises toward infinity. The final moments of a black hole evaporation are theorized to be an explosion, a burst of high-energy particles and radiation. Tiny, in terms of total energy, but dramatic in terms of temperature. From the coldest, self-luminous objects in the universe, Hawking temperatures of billionths of a Kelvin to a final explosive temperature spike, cold to hot in a final act. The thermal physics of black holes connects quantum mechanics to thermodynamics to general relativity in ways that physicists find simultaneously beautiful and deeply confusing. There is a problem called the black hole information paradox. When you drop an object into a black hole, the information about that object, the quantum mechanical state of every particle it was made of, appears to be lost. If the black hole eventually evaporates entirely, the information about everything that ever fell in seems to be gone. This violates a fundamental principle of quantum mechanics, which says information cannot be destroyed. Where does the information go? We don't know. Hawking himself wrestled with this question for decades, changing his position multiple times. Current understanding suggests the information is somehow encoded in the Hawking radiation, scrambled beyond recognition, but preserved. But the mathematics of exactly how this happens is still not fully worked out. The thermal physics of black holes, the coldest self-luminous objects in the universe, sits at the intersection of the deepest unsolved problems in physics. The fate of information at extreme cold, the behavior of quantum mechanics at extreme gravity, and what remains when the last black hole evaporates, and the universe is left with nothing but diffuse cold radiation. These are not idle questions. They are the questions that the greatest minds in physics are working on right now. And the cold of space, the fundamental coldness of the universe, is at the heart of all of them. There are regions and objects in space that push the limits further still, and in doing so, reveal unexpected truths about the relationship between temperature and the nature of matter. We spoke of the Boomerang Nebula and its 1 Kelvin interior. But there is another class of cold in the universe that operates on a completely different timescale. When a massive star, one with more than roughly 8 to 10 times the mass of the Sun, exhausts its nuclear fuel and collapses, the outer layers explode in a supernova. The inner core, crushed by gravity to a sphere roughly 10 miles across, becomes a neutron star. At the moment of collapse, temperatures in the core exceed 100 billion degrees Fahrenheit. 100 billion. Hotter than almost anything else that has existed in the universe since the first seconds after the Big Bang. The collapse produces a neutron star so dense that a single teaspoon of its material would weigh roughly 1 billion tons on Earth's surface. But neutron stars cool. In their first seconds and minutes, they radiate energy through neutrinos at a rate that strips away vast amounts of energy. Over thousands of years, they cool to temperatures of millions of degrees, still incomprehensibly hot by ordinary standards, but cooling. Over billions of years, they cool further. Old neutron stars, whose magnetic fields have decayed and whose accretion of new material has stopped, slowly radiate their heat into space. In the deep future, over timescales measured in quadrillions of years, even neutron stars will have radiated away nearly all their heat, settling into the cold background of an expanding, cooling universe. Like everything else in the cosmos, they are following the same trajectory. Everything cools. Everything moves toward the cold. There is a concept in thermodynamics that ties all of this together. A concept so fundamental that some physicists argue it is the most important principle in all of science. It is called entropy. In the most practical sense, entropy is a measure of disorder of how many ways the components of a system can be rearranged. In the most profound sense, entropy is the reason time flows in one direction. The second law of thermodynamics states that in an isolated system, entropy always increases. Disorder always grows. The universe moves in one direction, from order toward disorder, from hot toward cold, from concentrated energy toward diffuse equilibrium. This is not a tendency or a preference. It is a law, the most reliably obeyed law in all of physics. Heat always flows from hot things to cold things, never the reverse, without external energy input. Temperature differences always smooth out. Structures always decay. The universe moves, inescapably, toward greater and greater disorder. And the end point of that process, the state of maximum entropy for the universe, is the heat death. Not death in any dramatic sense. No explosion, no collapse, no singular catastrophic event. The heat death is the slow, inevitable consequence of the universe doing exactly what the second law demands. Every temperature difference in the universe is a reservoir of usable energy. Stars burning are temperature gradients, hot plasma against cold space. Life on Earth is sustained by the gradient between the Sun's 9,000-degree surface and the 2.7-degree cold of deep space. Every engine ever built, every weather system that has ever formed, every heartbeat, every thought, all of it runs on temperature differences. As the universe ages, these gradients are consumed. Stars burn their fuel and die. Galaxies grow dark. Black holes, which have accumulated the mass of millions and billions of stars, begin to slowly evaporate through a quantum mechanical process called Hawking radiation. A black hole of one solar mass has a Hawking temperature of around 60 billionths of a Kelvin colder than the cosmic microwave background, meaning such a black hole is actually absorbing more energy from the background radiation than it loses through Hawking radiation. But as the universe cools further and the background temperature drops, eventually even that changes. The black holes begin to lose energy faster than they gain it. They evaporate. Over timescales of 10 to the 67 years or more for a solar mass black hole. Far longer for the supermassive black holes at the centers of galaxies. Long after the last star has gone dark, long after the last neutron star has cooled toward the background temperature, long after every galaxy has dispersed and the stars have all burned out. Eventually, even the black holes evaporate, and the universe is left with diffuse radiation, scattered elementary particles, and nothing. No temperature differences. No gradients. No useful energy. The heat death. The temperature of the universe at that point will be indistinguishable from absolute zero. Not exactly absolute zero. The laws of thermodynamics may not permit exact absolute zero in a real physical system, but arbitrarily close to it. Colder than anything the universe currently contains anywhere. Current estimates suggest this final state lies somewhere around 10 to the 100 years in the future. 10 to the 100. A 1 followed by 100 zeros. The current age of the universe is 13.8 billion years, a number with 10 digits. 10 to the 100 has 101 digits. It dwarfs the current age of the universe by a margin so vast that ordinary language cannot convey it. But the direction is unambiguous. The universe is cooling, has been cooling since the moment of the Big Bang, when the entire observable cosmos was smaller than a proton and hotter than any number we can meaningfully write. And it has been falling in temperature every moment since. We live in what is, cosmologically speaking, a warm period, a brief, luminous, energetic phase between the fiery beginning and the cold, dark, silent end. The stars that light our sky are temporary. They are flames burning in a universe that is, overall and in the long run, cooling toward silence. To understand the cold the universe is headed toward, it helps to understand the heat it started with. The Big Bang was not an explosion in the conventional sense. There was no space for it to explode into. It was the beginning of space itself, the beginning of time. In the first fractions of a second after the beginning, the universe was unimaginably hot and dense. Temperatures exceeded 10 to the 32 Kelvin. That number is called the Planck temperature. It is believed to be the highest temperature that has any physical meaning under our current understanding of physics. Above the Planck temperature, quantum gravity effects become dominant, and our theories break down entirely. We do not know what happened at or before this moment. Our physics cannot reach there. From that unimaginable beginning, the universe cooled rapidly as it expanded. Within the first second, it had cooled to roughly 10 billion degrees. Still incomprehensibly hot, but a fraction of what it had been. During this early phase, the universe consisted of a dense, hot plasma, protons, neutrons, electrons, photons, and exotic particles we rarely encounter today. Within the first 3 minutes, it had cooled to around 1 billion degrees, cool enough for protons and neutrons to combine into the nuclei of light elements. Hydrogen nuclei, helium nuclei, traces of lithium. This is Big Bang nucleosynthesis, the origin of essentially all the hydrogen and helium in the universe today. Every hydrogen atom in your body, every hydrogen atom in the water you drink, every star in the sky, burning that hydrogen as fuel. All of it forged in the first 3 minutes of the universe, as the cosmos cooled from its primordial fire. For the next 380,000 years, the universe continued to cool but remained opaque. So hot and dense that photons could not travel more than a short distance before being scattered by the sea of charged particles filling space. The universe glowed with an intense light, but nothing could see through it. Then, at 380,000 years after the Big Bang, the universe had cooled to roughly 5,400 degrees Fahrenheit, or 3,000 degrees Celsius. At that temperature, electrons could combine with protons to form neutral hydrogen atoms for the first time. The universe became transparent. Photons could finally travel freely. For the first time, light could cross the cosmos without being immediately scattered. Those photons have been traveling freely ever since. 13.8 billion years. Stretched by the expansion of the universe from visible and infrared wavelengths to microwave wavelengths, cooled from 3,000 Kelvin to 2.725 Kelvin. Every microwave photon that Penzias and Wilson detected in 1964 had been traveling for 13.8 billion years. Each one carries the imprint of the moment the universe first became transparent. The moment light first moved freely through space. The cold we measure in the background of the cosmos is not just a temperature. It is the record of a journey across the full age of the universe. Every time you look at a clear night sky, you are looking through a universe filled with that ancient light. You cannot see it. It is in the microwave range, invisible to human eyes. But it is there, in every direction, in every cubic centimeter of space between you and the stars. The cold afterglow of creation. There is a period in the history of the universe that astronomers call the cosmic dark ages. It began about 380,000 years after the Big Bang, right at that moment of transparency we described, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was opaque. After that moment, it was transparent. But transparent is not the same as lit. The universe was transparent, and dark, and cold. There were no stars yet, no galaxies, no sources of light other than the fading glow of the cosmic background radiation itself. Just vast clouds of neutral hydrogen and helium gas, cooling and drifting in the dark. Slowly, under the influence of gravity, those clouds began to clump. Dense regions attracted more gas. The gas began to collapse. Over millions of years, tens of millions of years, the first structures began to form. Mini halos of dark matter, assembling from the subtle density differences left over from the Big Bang. Ordinary matter, hydrogen, and helium falling into those dark matter halos, concentrating, heating as it fell, and eventually, at the centers of the densest concentrations, reaching temperatures high enough to ignite nuclear fusion. The first stars. Astronomers estimate the first stars formed somewhere between 100 million and 200 million years after the Big Bang. We have not directly detected them yet. They are too far away, their light too redshifted by the expansion of the universe, their emission too faint for instruments we currently have. The James Webb Space Telescope is searching for them. The first stars were different from any stars that exist today. They formed from pure hydrogen and helium, no heavy elements, and they were enormous. Estimates suggest the first stars may have had masses tens or even hundreds of times the mass of the Sun. Stars that massive burn through their fuel extraordinarily quickly. They lived perhaps 1 million years. Then they exploded. Supernovae that scattered the first heavy elements, carbon, oxygen, silicon, iron, into the surrounding gas, enriching it, making the next generation of star formation possible, making chemistry more complex, making planets possible, making life possible. All of this happened against the backdrop of the cooling universe. From that initial 3000 Kelvin transparency to the first stars igniting in the dark, the universe cooling as it formed its first structures. The Dark Ages were not empty. They were a time of slow, cold assembly. Gravity working in the dark. Matter falling into patterns. Temperature gradually organizing itself into gradients, creating the first places where warmth could exist against the cold. This transition from the uniform cold of the post-recombination universe to the first lit islands of stellar warmth is called the epoch of reionization. As the first stars formed and burned, they produced intense ultraviolet radiation. That radiation ionized the surrounding neutral hydrogen, stripping the electrons away from the atoms that had combined just a few 100 million years earlier. The universe went from neutral to ionized again. Not uniformly and instantly, but in bubbles. Each early star or galaxy creating a growing sphere of ionized hydrogen around it. Those spheres grew and merged over hundreds of millions of years, until most of the hydrogen in the universe was ionized again. This process completed roughly 1 billion years after the Big Bang. It was the end of the Dark Ages. The universe was lit. But the cold, the deep, baseline cold of the cosmic background was still there. Still falling. Still pressing against every warm thing from all directions. The stars were not making the universe warm. They were making local exceptions. Tiny, brilliant, hot exceptions in an ocean of cold that stretched for billions of light years in every direction. That has always been the situation. That remains the situation today. The warmth of stars, scattered across a cold cosmos, separated by voids so vast that the average temperature of the universe, accounting for all that empty space, remains barely above absolute zero. Every star you see in the night sky is an island. Every galaxy is an archipelago. And between the islands, the cold holds. Ancient, patient, and absolute. Let's zoom back down to something closer to home. Because there is one more piece of this story, one more way, that the cold of space touches something tangible that most people never consider. Cold preserves. You know this from everyday experience. A freezer extends the life of food by slowing the chemistry that breaks it down. Cold museums preserve historical artifacts that would degrade quickly at room temperature. Biological samples are stored at very low temperatures to keep them unchanged for future study. In space, this preservation effect operates on a cosmic scale, and what it preserves is extraordinary. Comets are, in essence, ancient frozen debris, rocky, irregular bodies composed of ice, dust, and organic compounds that formed in the outer solar system roughly 4.5 billion years ago, when the solar system was still assembling itself from a swirling cloud of gas and dust. Because they spend the overwhelming majority of their time in the cold outer reaches of the solar system, far beyond the orbits of the outer planets, in the Kuiper Belt or in the more distant theoretical region called the Oort cloud. The material inside them has barely changed since the solar system was young. Cold has held them in place, chemically speaking, for 4.5 billion years. When a comet occasionally gets nudged into an orbit that brings it close to the Sun, it heats up. The ice on and near its surface vaporizes, a process called sublimation, releasing gas and dust into space that forms the comet's visible coma and tail. But the interior of the comet, the material that has never been close to the Sun, remains frozen and essentially unchanged. Scientists study comets because they are time capsules. The molecules locked in their ice are the same molecules that existed when Earth was still being assembled from smaller planetesimals. The Rosetta mission of the European Space Agency, which orbited the comet 67P/Churyumov-Gerasimenko from 2014 to 2016, and deployed a small lander onto its surface, detected glycine in the comet's outgassing material. Glycine is an amino acid, one of the building blocks of proteins, and the simplest amino acid found in the standard genetic code, preserved in frozen comet ice for 4.5 billion years. Formed originally, almost certainly, through the quantum chemistry of cold molecular clouds, and then locked in ice for the entire history of the solar system. This is what the cold of space does. It doesn't just destroy and freeze and stop. It holds things exactly as they are, for timescales that dwarf the history of life on Earth. There is a theoretical structure called the Oort cloud, a vast, roughly spherical shell of icy bodies, believed to surround the solar system at distances of several thousand to perhaps 100,000 times the Earth-Sun distance. The outer edge of this cloud would sit roughly 1 to 2 light-years away, nearly halfway to the nearest star. The objects in the Oort cloud are believed to have formed in the inner solar system billions of years ago, and been gravitationally scattered to their current cold, distant positions by the giant planets over the history of the solar system. Out there, in temperatures approaching the cosmic background, close to 2.7 Kelvin, those icy bodies have been drifting for 4.5 billion years, unchanged, preserved. their surfaces lightly processed by cosmic rays and ultraviolet light from distant stars, but their interiors essentially frozen in time from the moment the solar system formed. If we could reach them, and with current technology, we cannot. Not in any human lifetime. They would contain some of the most pristine material from the early solar system, chemistry from 4.5 billion years ago. Molecules assembled in the cold between stars before our sun even existed. The Voyager probes, which are the fastest objects humanity has ever sent into deep space, would take approximately 300 years just to reach the inner edge of the Oort cloud, and tens of thousands of years to cross through it. The cold of the outer solar system is not a wall. It is an archive, patient and vast and waiting. There is something worth pausing on here. We've spoken about the cold of space as though it is a single thing, a uniform condition, 2.7 degrees above absolute zero, everywhere. But cold in the universe is not uniform. It is structured. It has geography. Consider what we know. The surface of the sun, 9,940 degrees Fahrenheit. The corona, millions of degrees. The inner solar system, warm enough for liquid water. The outer solar system, cold enough to freeze carbon dioxide and nitrogen. Interstellar space, 2.7 Kelvin. The interiors of dense molecular clouds, 1 Kelvin or below. The coldest laboratory on Earth, 100 picokelvins. These are not just different points on a scale. They represent different physical regimes, different sets of rules. In the corona, matter exists as a plasma, electrons and ions completely separated, interacting electromagnetically in ways that solid and liquid matter cannot. In the photosphere, the temperature is hot enough to ionize some atoms, but not others, creating the absorption line spectrum that astronomers use to determine the chemical composition of stars. At room temperature, molecules bond, chemistry operates, life becomes possible. At the temperatures of the outer planets, hydrocarbon chemistry produces exotic results. At 1 Kelvin, quantum tunneling drives chemistry on grain surfaces. At 100 picokelvins, quantum mechanics operates on macroscopic scales. The universe does not have one cold. It has many colds, each with its own physics, each revealing a different aspect of the nature of matter and energy. And the transition between them, the way the universe's physical behavior changes as temperature changes, is itself one of the most profound things physics has ever uncovered. These transitions are called phase transitions. Not just the familiar ones, water freezing, water boiling, but deeper ones. The transition from plasma to neutral gas that happened 380,000 years after the Big Bang. The transition from normal matter to superfluid matter in liquid helium at 2.17 Kelvin. The transition from normal conductor to superconductor in certain metals at a few Kelvin. The predicted transition in the very early universe, when the electroweak force separated into electromagnetism and the weak nuclear force. As the universe cooled below roughly 10 to the 15 Kelvin in the first tiny fractions of a second. And before that, the separation of the strong nuclear force from the electroweak force at even higher temperatures. The entire history of the universe, from the Big Bang to the present day, can be told as a story of phase transitions driven by cooling, each transition creating a new regime of physics. Each regime creating new possibilities for matter and energy. The cold of the present universe is not the end state of a random process. It is the cumulative result of 13.8 billion years of phase transitions, each one changing what the universe is, what matter can do, and what structures can exist within it. We live in the phase where stars can burn, planets can form, and chemistry can organize itself into life. It is not the only phase the universe has passed through. It is not the phase the universe will be in forever. But it is the phase in which we find ourselves. And understanding that we are embedded in a particular thermal era, one defined by temperature